Dawn, January 5, 1943. Guadalcanal. Lieutenant Commander Red Cochran stands at his station aboard the cruiser USS Helena, scanning the horizon through binoculars still wet with spray. The ship is part of a task force escorting transport's valuable, vulnerable cargo ships carrying supplies to marine positions ashore. The radar operator's voice crackles over the intercom. 4 contacts. Inbound. Japanese dive bombers. Cochran has been at this for months now. He knows the rhythm of it. The waiting. The sudden acceleration of heartbeat when contacts appear. The almost mechanical process of tracking, aiming, firing. The sick feeling afterward, whether you hit or missed. His battery 5-inch guns mounted aft had been firing anti-aircraft rounds for the entire Guadalcanal campaign. The statistics were depressing. On average, it took somewhere between 500 and 1,000 rounds of 5-inch ammunition to bring down a single aircraft, sometimes more. The mathematics of it were simple and brutal. A shell fired at an aircraft traveling 300 miles per hour had to explode within roughly 30 feet of the target to inflict damage. The gunner had to estimate the aircraft's altitude, speed, and trajectory, then set a mechanical timer on the shell's fuse accordingly. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. If any variable was wrong, if the pilot changed altitude, if the range calculation was off by even a second, the shell would detonate harmlessly in empty sky. Pearl Harbor had demonstrated the inadequacy of this system with devastating clarity. American anti-aircraft batteries had fired thousands of rounds at attacking Japanese aircraft. The hit rate was well below 1%. But this morning, Cochran's battery had received something different: new ammunition. The shells looked identical to standard 5-inch rounds, but the paperwork called them Mark 32 special fused projectiles. No explanation of what made them special, no change in firing procedures, just instructions to use them and report results. The 4 Aichi D-3, a dive bomber's Allied reporting name VAL, emerged from the cloud layer. They were older aircraft by 1943 standards, but their pilots were experienced. One peeled off and dove toward the New Zealand cruiser Achilles. The bomb struck home. Achilles reported casualties and damage but remained operational. The surviving VALs turned to depart, climbing as they went. Cochran's guns tracked them. Standard procedure was to fire a salvo of 3 or 4 rounds, hoping probability would deliver at least one shell close enough to matter. But he'd been ordered to test these new projectiles, so he gave the command to fire. 2 shells. The second one detonated perhaps 50 feet from the nearest VAL. The aircraft didn't just take damage, it disintegrated. One moment it was a functioning machine with a pilot aboard. The next moment it was falling debris. Cochran lowered his binoculars slowly. In 2 years of naval service, he had never seen a shell explode like that. A perfect airburst at exactly the right distance without any visible impact. The timing was impossibly precise. His crew was staring at him. He could see the same confusion on their faces. How had that shell known when to detonate? "Reload," he said. "Same ammunition. Track the next target. Another VAL. Another burst. Another kill." By the time the engagement ended, Cochran's battery had expended perhaps a dozen rounds and claimed 2 certain kills. The ratio was unheard of. The after-action report he filed that afternoon contained a single underlined sentence: "The value of the Mark 32 fused projectile cannot be too highly stressed." What Lieutenant Commander Cochran didn't know what he couldn't know, because the information was classified at the highest level, was that inside each of those shells was a device that represented one of the most significant technological achievements of the war. A miniature radio transmitter and receiver, 5 vacuum tubes smaller than a human finger, a battery that created itself at the moment of firing, all packed into a space the size of a coffee cup, designed to survive being shot from a cannon and then operate flawlessly while spinning at 25,000 revolutions per minute. The proximity fuse, what the US Navy euphemistically called the variable time fuse, to disguise its true function. What the Japanese would come to call, in their reports and journals, the demon shell, This is the story of how it came to exist, and why, by 1945, Japanese pilots would refuse missions rather than face this weapon they could not understand and could not defeat. The problem was older than the war itself. Anti-aircraft artillery had existed since the First World War, when fighters and bombers first became significant weapons. The challenge has always been the same. How do you hit a fast-moving target in three-dimensional space when your projectile takes several seconds to reach altitude? The answer, in 1940 and earlier, was timed fuses, a mechanical device, set before firing, that would trigger the shell's detonation after a predetermined interval. The gunner estimated the target's altitude and calculated how long the shell would take to reach that height. The fuse was adjusted accordingly. Then the shell was loaded and fired. When everything worked perfectly, when the range estimation was accurate, when the fuse mechanism functioned precisely, when the aircraft maintained a predictable course, the shell would explode near the target and the shrapnel would inflict damage. But everything rarely worked perfectly. Aircraft were not predictable. Pilots took evasive action. They climbed or dove. They used clouds as cover. The human eye, even aided by optical rangefinders, struggled to judge altitude accurately. Mechanical fuzzes had inherent variability. Manufacturing tolerances meant that even identically set fuzzes might detonate seconds apart. The result was what had been observed at Pearl Harbor and in every naval engagement since. Thousands of shells fired, very few hits. The American military knew this was a problem well before the war began. In 1938, the Navy's Bureau of Ordnance had commissioned a study on improving anti-aircraft effectiveness. The report, completed in 1940, concluded that without a fundamental breakthrough in fuse technology, surface ships would remain dangerously vulnerable to air attack. The British had reached the same conclusion. Their researchers had gone further, actually developing preliminary designs for what they called a proximity fuse, a device that would automatically detect its distance from a target and detonate at the optimal moment. In August of 1940, as the Battle of Britain raged, a British technical mission arrived in Washington carrying blueprints and prototypes of their most secret military technologies. Among them was the preliminary design for a radar proximity fuse. This design arrived as part of what became known as the Tizard mission, named after Sir Henry Tizard, the scientist who led the delegation. The British were sharing their most closely guarded secrets, including the cavity magnetron that would revolutionize radar, because they recognized that only American industrial capacity could turn these concepts into mass-produced weapons. The proximity fuse design was brilliant in concept. A miniature radio transmitter in the shell's nose would emit a continuous signal. That signal would reflect off any metal object such as an aircraft and return to a receiver in the fuse. As the distance between shell and aircraft decreased, the frequency of the reflected signal would shift due to the Doppler effect. When that shift reached a certain threshold, indicating the target was close enough, the fuse would trigger detonation. It was brilliant in concept. It was also, by any reasonable assessment, impossible to build. Radio technology in 1940 was not miniature. A standard military radio weighed 50 pounds and filled a backpack. The transmitter and receiver used vacuum tubes, fragile glass components the size of light bulbs. Power came from heavy batteries. The entire assembly was sensitive to shock and required careful handling. Now imagine trying to fit all of that into a 5-inch artillery shell. Then imagine subjecting it to an acceleration of 20,000 times Earth's gravity as the shell was fired. Then imagine it had to function while spinning at 25,000 revolutions per minute, fast enough that centrifugal force would generate stresses that would tear apart any conventional electronic component. The British design was theoretically sound. But Britain lacked the industrial capacity and resources to actually manufacture such a device at scale. They were fighting for survival. Their factories were building fighters, bombers, tanks, ships' immediate needs. A proximity fuse was a long-term research project that might take years to perfect, so they gave the blueprints to America and hoped American industry could make it real. The National Defense Research Committee was created in June of 1940, months before America entered the war. Its purpose was to mobilize civilian scientific expertise for military problems. The chairman was Vannevar Bush, an electrical engineer and inventor who had spent his career developing analog computers and advocating for the application of scientific research to practical problems. Bush understood something that many military planners did not: that modern warfare was increasingly a contest of technology. Radar, sonar, code breaking, advanced metallurgy, electronics. These were becoming as important as tactics and strategy, and the people best equipped to develop these technologies were not necessarily in uniform. When the British proximity fuse design arrived in Washington, Bush assigned the project to Section T of the National Defense Research Committee. Section T was focused on ordnance shells, bombs, fuses, explosives. Its director was Dr. Merle Anthony Tuve. Tuve was 40 years old in 1940. He had a doctorate in physics from Johns Hopkins and had spent his career studying the ionosphere and cosmic rays at the Carnegie Institution's Department of Terrestrial Magnetism in Washington. He was an experimentalist, someone who built equipment, designed tests, got his hands dirty in the laboratory. He had published significant research on nuclear physics and had helped develop techniques for measuring the height of the ionosphere using radio waves. He had no background in weapons development and had never worked on military hardware. That was exactly why Bush chose him. The military had been trying to solve the proximity fuse problem for years using conventional approaches. All had failed. Bush needed someone who didn't know what was supposed to be impossible. Tuve accepted the assignment with some reluctance. He was a pacifist by inclination, uncomfortable with the idea of developing weapons. But like many scientists of his generation, he had come to believe that the threat posed by Nazi Germany and Imperial Japan justified setting aside those reservations. If American democracy was going to survive, it needed the best possible tools of defense. He assembled a small team at Carnegie in late 1940. The initial group included fewer than a dozen people: physicists, electrical engineers, and technicians. Their first task was to evaluate whether the British design was even feasible. They spent 2 months reviewing the blueprints and conducting preliminary experiments. The conclusion was sobering. The British concept was sound, but the practical challenges were extraordinary. 3 problems in particular seemed almost insurmountable. First, the vacuum tubes. Every radio of that era relied on vacuum tubes to amplify signals. These were glass envelopes containing metal filaments and grids, evacuated of air to allow electrons to flow freely. They were inherently fragile. Drop one on the floor and it would shatter. The idea of building tubes that could survive being fired from a gun, surviving an instantaneous acceleration that would crush a human being, seemed absurd. Second, the power supply. Vacuum tubes required electrical current. Batteries of the period used liquid electrolytes and were heavy, temperature-sensitive, and unreliable. How could you design a battery that would survive gun launch, function in tropical heat or Arctic cold, remain stable in storage for months, and then activate instantly when needed? Third, the entire system had to be manufacturable at massive scale and low cost. This wasn't a laboratory curiosity. If it worked, the military would need millions of them. Each fuse had to cost no more than $20, about $400 in today's currency. It had to be simple enough that factory workers with minimal training could assemble it. It had to be reliable enough that sailors could load and fire it without special procedures. Oh, and it had to be ready for combat deployment within 2 years. Tuve looked at his team. They looked back at him. Nobody spoke for a long moment. Then Richard Roberts, one of the senior physicists, said what everyone was thinking. "This is impossible." Tuve nodded slowly. "Yes, it probably is, but we're going to try anyway, because there isn't a better option. The Navy needs this. If we don't solve it, thousands of sailors are going to die in attacks we could have prevented." "Where do we even start?" another engineer asked. "With the hardest problem," Tuve replied. "The tubes. We figure out how to build a vacuum tube that won't break. Everything else depends on that." James Alfred Van Allen was 26 years old when he joined Section T in January of 1941. He had just completed his doctorate in physics at the University of Iowa, studying cosmic rays and nuclear physics. He was a quiet man, methodical, known among his colleagues for building his own experimental equipment because commercial instruments never quite met his exacting specifications. Fuze assigned him what seemed like the most impossible problem: design a vacuum tube that could survive being shot from a 5-inch naval gun. Van Allen began by studying the smallest tubes available in 1941. Hearing aid tubes. These were miniaturized compared to standard radio tubes, perhaps an inch tall, and were designed to be relatively rugged since hearing aids were worn on the body and subject to movement and occasional drops, but they were still far too large for a 5-inch shell nose, and they were nowhere near strong enough to survive gun launch. Van Allen obtained several dozen hearing aid tubes from Western Electric and Raytheon and began systematic destruction testing. He built fixtures that could simulate the acceleration and spin of a fired shell devices that used compressed air or springs to generate enormous forces in fractions of a second. He mounted tubes in these fixtures and subjected them to progressively higher forces until they broke. Each time, he carefully recorded exactly how the tube failed. The glass cracked at certain stress points, the filaments snapped, the internal supports buckled, the connections between components sheared apart. Each failure taught him something. Glass thickness mattered, but not uniformly. Some areas needed reinforcement, others needed flexibility to absorb stress. The filaments needed support structures, but those structures couldn't be so rigid that they'd transfer too much force to the delicate wires. The entire tube assembly had to be designed so that centrifugal force actually helped hold components in place rather than tearing them apart. He spent 4 months on this. He worked alone, mostly, in a small laboratory space at Carnegie. The work was tedious and precise. He was essentially learning, through trial and error, how to build something that had never existed before. His hands developed chemical burns from handling the acids used in glass etching. His eyes strained from the precision work of manipulating components that were fractions of an inch in size. He filled notebook after notebook with detailed sketches and measurements. By April of 1941, he had a design that survived about half the time. By June, 60%. By August, 75%. But Fuze needed 90% reliability or better for the fuse to be militarily useful. A weapon that failed 1 time out of 4 was worse than useless. It was dangerous to the gun crews, wasted manufacturing resources, and couldn't be trusted in combat. Van Allen went back to the laboratory. He tried different glass formulations. He experimented with various support structures. He tested different filament materials and configurations. Progress was incremental, measured in percentage points gained over weeks of work. Years later, in his private notes discovered after his death in 2006, he wrote about this period. "I was young enough to think that impossible was just another word for difficult. Every tube that failed taught me something. I'd examine the wreckage under a microscope, identify the failure point, redesign that component, and try again. Progress was incremental, frustrating, but it was progress. I remember the night I got to 85%. I should have been elated. Instead, I remember sitting in the lab at 2 in the morning, staring at 15 broken tubes, trying to understand why 15% still failed. I remember thinking, somewhere in the Pacific, sailors are dying because I can't figure this out. That thought kept me working." He achieved 90% reliability in October of 1941, 2 months before Pearl Harbor. The final design was a tube about half an inch tall and a 1/4 inch in diameter, smaller than anything that had existed before in vacuum tube technology. The glass was thicker in strategic locations. The internal components were suspended in a way that allowed slight movement without breaking. The filaments were made of tungsten wire reinforced at stress points. It was a marvel of miniaturization and engineering, but it was only one component. The fuse needed 5 of these tubes, plus dozens of other parts, all working together in an integrated system. While Van Allen struggled with vacuum tubes, Lloyd Berkner tackled the power supply problem. Berkner was 35 years old, an electrical engineer and physicist who had worked with Admiral Richard Byrd on Antarctic expeditions in the 1930s. He'd been responsible for developing and maintaining radio equipment that could function in temperatures that routinely dropped to 50 below zero. He understood better than most how batteries failed under stress. He'd seen it firsthand in conditions where failure meant loss of communication and potential death. The fundamental problem was this: conventional batteries of the era were simply incompatible with the demands of the proximity fuse. They used liquid electrolytes, typically sulfuric acid solutions that would spill or freeze. They were heavy. They degraded over time in storage, losing charge even when not in use. They were activated from the moment of manufacture, meaning they had a limited shelf life. A proximity fuse battery had to do something no battery of that era could do: remain completely inert in storage, survive the shock of being fired from a gun, then activate instantly and provide steady current for the few seconds the shell was in flight. Berkner's solution was elegant and radical. Don't build a battery that survives gun launch. Build a battery that doesn't exist until gun launch creates it. His design used a sealed glass ampule about the size of a pencil eraser, filled with liquid electrolyte solution. Around this ampule, in a precise spiral arrangement, were thin plates of carbon and zinc, the components of a standard battery, but not yet in contact with the electrolyte. The entire assembly was inert. No chemical reaction was occurring. It could sit in storage indefinitely without degradation. It was immune to temperature extremes. It was lightweight. The theory was simple. When the shell was fired, the enormous acceleration, 20,000 times the force of gravity, would shatter the glass ampule instantly. The liquid electrolyte, forced outward by centrifugal force from the shell's spin, would flow into the gaps between the spiral plates. The moment the liquid made contact, the chemical reaction would begin. Electrons would flow. The battery would activate itself, creating voltage in the milliseconds after firing, just as the radio transmitter needed power. It was brilliant. It was also extremely difficult to get right. The glass ampule had to shatter at precisely the right moment, and in precisely the right way. Too strong, and it wouldn't break during gun launch. Too weak, and it might break during shipping or handling, causing the battery to activate prematurely and corrode itself before it was ever used. The spiral plates had to be positioned so that centrifugal force would distribute the electrolyte evenly, no dry spots, no pooling. The chemical composition of the electrolyte had to be optimized for instant activation and sustained output. Berkner built prototype after prototype. The first 50 all failed in various ways. The glass didn't break, or it broke too early during handling, or it broke but the electrolyte didn't flow correctly, or the voltage was too low, or the chemical reaction was too slow to provide power when needed. He kept meticulous records of every test. Each failure was documented, analyzed, and understood. He'd adjust one variable, glass thickness, or spiral spacing, or electrolyte concentration, and test again. Then another variable, then combinations of variables. By December of 1941, just as America entered the war, he had achieved an 85% success rate. Good, but not good enough. The same threshold Fuze had set for Van Allen's tubes, 90% or better. Berkner reached that threshold in January of 1942, 13 months after starting the project. The final design used a specially formulated glass with precise thickness, an electrolyte solution that remained liquid across a wide temperature range, and a spiral plate arrangement that ensured even distribution under the specific centrifugal forces generated by a 5-inch shell's rotation. While Van Allen and Berkner worked on components, other members of the team tackled the radio circuits themselves. Richard Roberts led this effort. He and several colleagues built on the British design but refined it significantly. The circuit had to generate a radio signal at a precise frequency, approximately 180 MHz, in the VHF band, and had to do so using components that could withstand gun launch. The transmitter used one of Van Allen's miniature vacuum tubes as an oscillator. This tube would generate a continuous radio wave that was broadcast from a small antenna built into the fuse nose. The signal would reflect off any metal object within range, such as an aircraft, and return to the fuse. The receiver circuit had to detect this reflected signal, compare it to the transmitted signal, and measure the frequency shift caused by the Doppler effect. This shift occurred because the shell and the target were moving relative to each other. As they approached, the reflected signal's frequency would increase slightly. When that shift reached a predetermined threshold, indicating the target was close, enough for the shell's explosion to cause damage, the circuit would close a switch. That switch would trigger a small electrical detonator, which in turn would set off the main explosive charge in the shell. All of this had to happen in fractions of a second. The shell was traveling at roughly half a mile per second. The window for optimal detonation was measured in milliseconds. The circuits had to be fast, reliable, and simple enough to manufacture cheaply. Roberts and his team spent months refining the circuit design. They tested hundreds of configurations, looking for the optimal balance of sensitivity, reliability, and manufacturability. By spring of 1942, they had a working design that could detect aircraft at distances up to roughly 70 feet, the optimal range for a 5-inch shell's shrapnel pattern. By spring of 1942, Section T had working prototypes of all major components: vacuum tubes that survived gun launch, batteries that activated themselves at the moment of firing, transmitter and receiver circuits that functioned under extreme conditions. Now comes perhaps the most difficult challenge: integration. Putting all these components together in a package small enough to fit in a shell nose, rugged enough to survive combat conditions, reliable enough for military use, and simple enough to manufacture by the millions. Fuze's team, which had by now grown to several dozen people, had exceeded the capacity of the Carnegie Institution facility. The work required more space, more equipment, and more security. The NDRC, with Navy support, moved the entire operation to a leased building in Silver Spring, Maryland, a 3-story structure that had previously housed an automobile garage on the ground floor and Social Security Administration offices on the upper floors. This became the Applied Physics Laboratory, APL. The name was deliberately vague, nothing about fuses or weapons or proximity detection, just applied physics. The building was surrounded by security fences. Armed guards checked credentials at the entrance. Workers were told not to discuss their jobs with anyone, even family members. Fuze was given extraordinary authority. He could hire anyone he needed. He could commandeer equipment from other facilities. He could bypass normal procurement processes if speed was essential. The Navy had decided that the proximity fuse was absolutely critical to fleet survival in the Pacific, and bureaucratic obstacles were simply swept aside. By summer of 1942, APL had assembled complete fuses, working prototypes that integrated all the components into a functional device. The Mark 32 proximity fuse, as it was designated, looked almost deceptively simple. A cylinder about 4 inches tall and 2 inches in diameter, with a rounded nose. Inside that package were 130 separate components, including 5 vacuum tubes, a self-activating battery, a radio transmitter, a receiver, amplifier circuits, a detonator, and multiple safety mechanisms. The safety mechanisms were particularly important. The fuse had to be completely inert until fired. It couldn't detonate during shipping, handling, or loading, even if dropped or struck. It had to arm itself only after the shell left the gun barrel, giving enough distance that an accidental detonation wouldn't endanger the gun crew or nearby ships. This was accomplished through an elegant mechanical system. A small propeller on the fuse nose would begin spinning as the shell flew through the air. After roughly 0.7 of a second of flight, by which time the shell was several hundred yards from the ship, the spinning propeller would mechanically disengage a safety lock. Only then would the electrical circuits become active and capable of triggering detonation. Testing began immediately. August 12, 1942, Chesapeake Bay. The light cruiser USS Cleveland was on its shakedown cruise, the series of sea trials that would determine whether the newly commissioned ship was ready for combat operations. The crew was systematically testing every system: engines, steering, communications, damage control, weapons. But this particular test was unusual. 3 radio-controlled drone aircraft had been deployed in the bay. These were essentially pilotless planes BQ series target drones that could be directed from a control station aboard ship to fly specific patterns at various altitudes. They were used routinely for anti-aircraft gunnery practice, giving gun crews live targets to track and engage. Cleveland's 5-inch guns were loaded with a mix of ammunition provided by APL, Half were standard shells with mechanical time fuses, half were special test rounds shells equipped with the new Mark 32 proximity fuses. The test plan called for 2 full days of firing. The drones would fly various patterns straight and level, evasive maneuvers, approach runs at different angles and speeds. The gunners would engage using both types of ammunition, and the results would be carefully documented. The Navy needed to know whether these new fuses actually worked under conditions that approximated combat. The test lasted 4 hours. The first drone was destroyed with 2 shells, both proximity fused, both detonated in perfect airbursts without physically hitting the target. The second drone, destroyed with a single shell, a proximity fuzzed round that exploded perhaps 40 feet from the aircraft, close enough that the shrapnel pattern shredded the drone's control surfaces and caused it to crash. The third drone, destroyed with a single shell, 4 shells fired, 3 drones destroyed, no direct hits required. Every proximity-fused round had functioned exactly as designed. The observers, including Captain Russell Berkey and several officers from the Bureau of Ordnance, stood in stunned silence for a moment. Then Berkey grabbed the nearest communications officer and dictated an urgent dispatch. The test exceeded all expectations. Recommend immediate authorization for large-scale production. This weapon will fundamentally change naval anti-aircraft capability. Request priority assignment of manufacturing facilities. The test that was supposed to last 2 days had been completed in 4 hours because there were no more drones to shoot at. The proximity fuse worked. The Bureau of Ordnance moved with unusual speed. Within days, production orders were placed with multiple manufacturers, but producing these fuses at the scale the Navy needed posed enormous challenges. Each Mark 32 fuse contained 130 separate components, 5 vacuum tubes, dozens of resistors, capacitors, and other electronic parts. The self-activating battery, the detonator, the safety mechanisms, all had to be manufactured to precise tolerances. Variations of thousandths of an inch could cause the fuse to fail, and the Navy wanted them by the hundreds of thousands, eventually by the millions. Fuze and his team at APL had proven the concept worked. Now they had to transform a laboratory prototype into a mass-produced weapon. This meant working with American industry to set up production lines, develop quality control procedures, train workers, and solve the inevitable problems that arose when scaling up from a dozen hand-built prototypes to tens of thousands of fuses per week. Over 80 companies were eventually involved in proximity fuse production. Major electronics manufacturers like RCA, General Electric, Raytheon, Sylvania, and Westinghouse produced vacuum tubes and electronic components. Eastman Kodak, despite being primarily a photography company, contributed its expertise in precision manufacturing. Even Wurlitzer, the organ and jukebox company, manufactured components requiring precise mechanical work. The production process was compartmentalized for security. Most workers had no idea what they were building. A factory in one state might produce vacuum tubes. Another factory in another state produced battery components. A third assembled circuit board. Final assembly happened at yet another facility. Very few people saw the complete fuse or understood its function. The official designation variable time fuse was deliberately misleading. It suggested an improved mechanical timer, not a revolutionary proximity detection system. Workers were told they were building an advanced time fuse that required precision manufacturing. They weren't told about the radio transmitter, the proximity detection, or how the fuse actually worked. This secrecy was considered essential. If the Germans or Japanese captured an intact fuse and reverse-engineered it, they might develop their own version, or worse, develop countermeasures. A simple radio jammer could potentially render the fuses useless. The entire advantage would be lost. By December of 1942, the first combat-ready proximity fuzzes were being delivered to ammunition depots in the Pacific. Production was still slow, only a few hundred fuzzes per day, but it was ramping up quickly. By early 1943, when Lieutenant Commander Cochrane fired those first combat rounds aboard USS Helena, production had reached several thousand fuses daily. By late 1943, It was 40,000 per day. By war's end, 22 million proximity fuzzes had been manufactured. The total cost exceeded $1 billion in 1940s currency, approximately $18 billion in today's money. This made it one of the most expensive weapons development programs of the war, exceeded only by the Manhattan Project's atomic bomb program. But on that January morning in 1943, as Cochrane's after-action report made its way through Navy channels, none of that massive industrial mobilization was visible to the gun crews using these new shells. They just knew that something had changed. Targets that would normally require hundreds of rounds to destroy were now being eliminated with a handful of shots. Helena's report reached Pearl Harbor within hours. Admiral William Halsey, commander of the South Pacific Force, read it personally. Halsey had been advocating for better anti-aircraft defenses for months. He'd seen too many ships damaged or sunk by Japanese air attacks. He'd watched gun crews fire until their barrels were too hot to touch, achieving almost nothing. He immediately sent a dispatch to Washington: require maximum production and priority delivery of Mark 32 fused ammunition. Combat results exceed all predictions. This capability is essential for fleet operations. Production priorities were adjusted. More factories were brought online. By March of 1943, every American warship in the Pacific was receiving allocations of proximity-fused ammunition. The standard loadout was roughly 25% proximity fuzzes, 75% conventional ammunition. This ratio balanced the new capability against the limited production capacity and the concern about fuzzes potentially being captured by the enemy. Gun crews were given minimal information. They were told these were improved fuses that didn't require setting, just load and fire. The shells would detonate automatically at the correct moment. Don't ask how they worked, just use them. And they did, with devastating effect. Throughout 1943, as American forces pushed westward across the Pacific, engagement after engagement demonstrated the proximity fuse's value. Japanese aircraft that had been able to press attacks home, despite heavy anti-aircraft fire, were now being destroyed at greater distances. The effective engagement range of 5-inch guns had essentially doubled. Before proximity fuses, heavy anti-aircraft guns like the 5-inch 38 caliber were most effective against aircraft at ranges of 3,000 to 5,000 yards, close enough for range estimation to be reasonably accurate. Beyond that, the target was too far away for timed fuses to be reliably set. With proximity fuses, effective range extended to 8 or even 10,000 yards. The shell didn't need a perfectly timed fuse setting, it just needed to pass close to the target. The fuse would handle the rest. Admiral Arleigh Burke, who commanded destroyer squadrons in the Solomon Islands campaign, wrote in his post-war memoirs about the impact. Mechanical time fuzzes which we had been using brought down aircraft at night essentially by accident. They were good for harassment, but that was about all. The new fuses, we weren't told what made them different, changed everything. Suddenly our guns were actually destroying targets with regularity. It was almost uncanny. Shells would explode at exactly the right moment, as if they knew where the aircraft was. They did know. That was the secret no one could explain to the gun crews. Japanese pilots began reporting strange phenomena. American anti-aircraft fire had become mysteriously accurate. Shells exploded at precisely the right altitude and distance, even when the aircraft was maneuvering. Some pilots attributed this to new radar fire control systems. Others suggested the Americans had developed some kind of homing shell. A few believed it was something supernatural. Japanese intelligence officers collected fragments of exploded American shells, trying to understand what had changed. But the fragments told them nothing. The fuse components were destroyed by the explosion. All that remained was twisted metal and shattered glass. The secret remained safe. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By October of 1944, the nature of Japanese air attacks had changed dramatically. Conventional bombing and torpedo runs had become prohibitively expensive in aircraft and pilot losses. American combat air patrols, guided by radar, intercepted most attacks before they reached the fleet. Those that got through faced a wall of anti-aircraft fire that was far more lethal than it had been a year earlier. So the Japanese adapted. If pilots were going to die anyway, if the odds of surviving an attack run and returning to base had dropped to nearly zero, then why not guarantee the attack would succeed by deliberately crashing into American ships? The Kamikaze Divine Wind was born out of desperation and pragmatism. A pilot flying a bomb-laden aircraft directly into a ship couldn't miss. The entire airplane became a weapon. Even if the aircraft was damaged, engine shot out, wings shredded, pilot dead, as long as it maintained enough momentum to reach the target, it would complete its mission. This changed the defensive equation fundamentally. Traditional anti-aircraft tactics aimed to damage aircraft, knock them off course, force them to abort their attack runs. But a kamikaze didn't need to be intact or controllable. It just needed to reach the ship. The only effective defense was complete destruction, vaporizing the aircraft before it could get close enough that its ballistic trajectory would carry the wreckage into the ship. And that required weapons that could kill reliably at maximum range. The proximity fuse became absolutely critical to survival. The Battle of Leyte Gulf, October 1944, marked the first large-scale use of kamikaze tactics. On October 25th, organized suicide units attacked American escort carriers of Taffy 3. The escort carrier Street Low was struck by a kamikaze and sank within 30 minutes. Several other carriers were damaged. The psychological impact was profound. Japanese pilots were deliberately crashing into ships, and conventional defenses seemed inadequate to stop them. Vice Admiral John McCain, commander of Task Force 38, sent an urgent assessment to Admiral Chester Nimitz. Kamikaze attacks represent a qualitatively different threat. Standard anti-aircraft doctrine assumes enemy pilots have survival instinct and will break off attacks when faced with heavy fire. Kamikazes do not break off. They must be completely destroyed. Require maximum allocation of proximity-fused ammunition for all fleet units. The Navy responded by increasing the proportion of proximity fuses in ammunition loadouts. By January of 1945, some ships were carrying 50% or more proximity-fused rounds. The doctrine evolved. Open fire at maximum range with proximity fuses. Attempt to destroy the incoming aircraft as far from the ship as possible. The statistics bore out the effectiveness. Analysis of anti-aircraft engagements between October 1944 and January 1945 showed that 5-inch guns, firing proximity-fused ammunition, required an average of 310 rounds to destroy one kamikaze aircraft. The same guns firing conventional time-fused ammunition required an average of 1,162 rounds per kill, nearly 4 times as many. Put another way, proximity fuses made anti-aircraft guns roughly 4 times more effective against kamikazes. In a combat environment where every second mattered, where a single aircraft getting through could sink or cripple a ship, that improvement was the difference between survival and catastrophe. But even with proximity fuses, the kamikaze threat remained terrifying. April 6, 1945. Off Okinawa. The invasion of Okinawa had begun on April 1st. The island was only 350 miles from the Japanese home islands, close enough that Japanese aircraft could strike American forces and still have fuel to return. The Japanese High Command had designated Okinawa as the site of a last-ditch defensive effort. They would throw everything they had at the American fleet, hoping to inflict such catastrophic losses that the United States would negotiate a peace rather than invade the home islands. Operation Tengo, the massed kamikaze attacks on the Okinawa invasion fleet, began on April 6th. Wave after wave of aircraft, hundreds at a time, hurled themselves at American ships. The destroyer USS Laffey was on radar picket duty, stationed 30 miles north of Okinawa to provide early warning of incoming raids. At 7:30 in the morning, radar detected a large formation approaching. Within minutes, 22 separate aircraft began attacking Laffey. The ship's gun crews went to work. 5-inch guns, 40mm mounts, 20mm cannons, every weapon that could bear opened fire. The 5-inch guns were loaded almost exclusively with proximity-fused ammunition. The gunners fired as fast as the loaders could work. The sky around Laffy filled with black clouds, the detonations of proximity-fused shells, creating a barrier of shrapnel between the ship and the incoming kamikazes. Aircraft exploded in mid-air. Others had wings blown off and tumbled into the sea. Some were damaged but maintained enough control to continue their dives. For 80 minutes, Laffy fought for survival. The gun crews fired until the barrels glowed red-hot. Shell casings piled up on deck. The air filled with smoke and the smell of burning propellant and hot metal. By the time the attack ended, Laffy had been hit by 6 kamikazes and 4 bombs, but she remained afloat. Her gun crews had destroyed 6 kamikazes, outright disintegrating them in mid-air before they could reach the ship. 4 more had been so badly damaged by proximity-fused bursts that they crashed into the sea short of their target, or hit glancing blows that caused less damage than a direct strike would have. Laffy's after-action report credited proximity fuses with saving the ship. Without them, more kamikazes would have gotten through intact. The ship would likely have sunk. Even so, 32 of Laffy's crew were killed, and 71 wounded. The ship was heavily damaged and had to be towed to a repair facility. The proximity fuse was not a miracle weapon. It could not make ships invulnerable. It simply improved the odds. Across the fleet at Okinawa, the same pattern repeated. Ships that survived did so in part because proximity fuses allowed them to destroy or damage attacking aircraft at greater ranges, but the sheer number of kamikazes overwhelmed defences. Between April and June of 1945, the Navy suffered its highest casualties of the Pacific War. 36 ships were sunk, 368 were damaged. Nearly 5,000 sailors were killed. Thousands more were wounded. The psychological toll was immense. Sailors knew that every time they went to battle stations, they might face aircraft flown by pilots with no intention of returning home pilots, who saw their own deaths as the price of taking American lives. Post-war analysis by the Navy's Operations Evaluation Group examined the effectiveness of various anti-aircraft systems at Okinawa. The conclusion was clear. Proximity-fused 5-inch shells were responsible for approximately half of all Japanese aircraft destroyed by naval gunfire, despite representing only about 35% of the ammunition expended. They were, round for round, significantly more effective than any other anti-aircraft weapon available. The report also noted that without proximity fuses, casualties would have been substantially higher. The analysts estimated that at least 15 additional ships would have been sunk, and casualties would have increased by perhaps 30 to 40%. The proximity fuse had not prevented the bloodshed at Okinawa, but it had limited it. Japanese pilots who survived kamikaze missions, those who turned back due to mechanical problems or inability to locate targets, reported their experiences to intelligence officers. These reports, captured after the war, provide insight into how the Japanese perceived American anti-aircraft defenses. One report from May of 1945 described American anti-aircraft fire as demon shells that know where aircraft are. The report noted that shells seemed to explode at precisely the optimal moment, even when aircraft were maneuvering unpredictably. It is as if the shells can see the aircraft and choose when to burst. This is not natural. This is not the work of machines alone. Another report used the term cursed ammunition and suggested that American forces had somehow weaponized supernatural forces. This wasn't superstition so much as confusion. The pilots had no frame of reference for understanding what they were experiencing. They knew that shells weren't supposed to detonate with such precision. They knew that timed fuses required accurate range estimation and couldn't adjust for maneuvering targets. What they were seeing violated their understanding of how anti-aircraft fire worked. The truth that the shells contained miniature radios that detected aircraft and automatically triggered detonation at the optimal moment was beyond their ability to discover, and it remained classified throughout the war, even after Japan's surrender. The proximity fuse's impact extended beyond the Pacific Naval War. In December of 1944, as German forces launched their surprise offensive in the Ardennes, the Battle of the Bulge, the U.S. Army finally received authorization to use proximity fuses in artillery shells. The Pentagon had resisted this for years. The fear was that if a proximity-fused shell failed to detonate and landed intact in German-held territory, enemy engineers might recover it, reverse-engineer the technology, and develop their own version. Or they might develop radio countermeasures, jamming signals that would render the fuses useless. But the situation in the Ardennes was desperate. German armoured divisions had broken through American lines and were pushing toward vital supply depots and communication centres. The weather was terrible. Heavy clouds and fog prevented air support. American infantry divisions were fighting at a severe disadvantage. General Dwight Eisenhower personally demanded that proximity fuses be released for artillery use. He argued that the tactical advantage outweighed the security risk. If the Germans overran American positions and captured fuses, that was a risk he was willing to accept. The alternative, losing the battle for lack of effective artillery, was unacceptable. The Pentagon agreed. On December 22nd, approximately 200,000 artillery shells equipped with proximity fuses were rushed to the front lines. These were primarily 105mm and 155mm shells, the standard field artillery calibers used by American forces. The impact was immediate and devastating. For German forces, traditional artillery shells buried themselves in the ground before exploding. The earth absorbed much of the blast energy. Fragmentation patterns were directed upward and outward from the point of impact, but the effectiveness was limited. Troops in foxholes or trenches had substantial protection. Proximity-fused shells detonated in airbursts, exploding 10 to 20 feet above the ground. The blast and fragmentation patterns spread outward in all directions. Troops in foxholes and trenches were now exposed to shrapnel raining down from above. Cover that had been effective against traditional artillery was largely useless against airbursts. The psychological impact was perhaps even greater than the physical casualties. German soldiers reported that American artillery had suddenly become far more deadly. Positions that should have provided protection didn't. The explosions seemed to happen at exactly the worst moment, close enough to inflict maximum casualties, but too high for the ground to provide any protection. One German after-action report, captured in January of 1945, described the effect. American artillery has become uncanny in its precision. Shells explode overhead at optimal height. Previous defensive positions are no longer adequate. Casualties from artillery fire have increased substantially. General George Patton, whose Third Army used proximity-fused artillery extensively during the Ardennes campaign, wrote in a letter to the War Department, "The new shell with the funny fuse is devastating. We caught a German battalion attempting to cross the Sauer River with a battalion-scale concentration and killed by actual count 702 men. I think that when all armies get this shell, we will have to devise some new method of warfare." Post-war analysis suggested that proximity-fused artillery shells were between 3 and 7 times more lethal than conventional time-fused or impact-fused shells, depending on terrain and circumstances. In open terrain against exposed infantry, the advantage could be as high as 10 to 1. The Germans did eventually capture intact proximity fuses. In late December of 1944, during the height of the Battle of the Bulge, German forces overran an American ammunition dump that contained approximately 20,000 proximity fuses for artillery shells. German intelligence officers examined the fuses carefully. They were baffled. The devices clearly contained electronic components, vacuum tubes and circuits were visible when the fuses were carefully disassembled. But German engineers couldn't understand how these components could possibly survive being fired from a gun. Their own research into proximity fuses, conducted throughout the 1930s, had concluded that it was impossible to build electronics rugged enough to withstand gun launch. They had abandoned the effort as impractical. Now they were looking at American fuses that clearly worked and were being mass-produced, yet the technology seemed impossible. Several theories circulated among German technical personnel. Some believed the fuses were a bluff, that they were actually just very sophisticated timed fuses, and the reports of their effectiveness were exaggerated for propaganda purposes. Others thought the Americans had discovered some revolutionary manufacturing technique that allowed vacuum tubes to be far stronger than German tubes. A few speculated that the devices used some unknown physical principle. None came close to the truth, which was that the Americans had simply spent 2 years solving seemingly insurmountable engineering problems through methodical experimentation and enormous investment of resources. The miniaturized vacuum tubes that Van Allen had developed were, in 1944, unique in the world. No other nation had anything comparable. By the time German engineers had figured out roughly how the fuzzes worked, spring of 1945, Germany was collapsing. There was no industrial capacity to manufacture copies, no time to develop countermeasures, no way to reverse the tide of the war. The proximity fuse remained an American advantage to the end. When the war ended in August of 1945, the proximity fuse program was gradually declassified. The full technical details remained secret for several more years, but the basic fact of its existence was made public. Articles appeared in technical journals describing it as one of the most significant weapons developments of the war. Vannevar Bush, in his 1947 report Science, the Endless Frontier, credited the proximity fuse with 3 major impacts on the war's outcome. It had been essential for defending the fleet against kamikaze attacks in the Pacific. It had been crucial in defending Britain against Von flying bombs, German cruise missiles, that had terrorized London in 1944, and it had significantly increased the effectiveness of American artillery in the final months of the European War. Secretary of the Navy James Forrestal stated publicly, "The proximity fuse has helped blaze the trail to Japan. Without it, our fleet casualties in the Pacific would have been substantially higher, and the pace of our advance would have been slower." British Prime Minister Winston Churchill, speaking in Parliament after the war, said, "These proximity fuses, made in the United States, proved potent against the small unmanned aircraft with which we were assailed in 1944, referring to the Von rockets. British anti-aircraft batteries using proximity-fused shells had achieved a destruction rate of approximately 79% against V1s by the end of the campaign. Before proximity fuses, the destruction rate had been below 30%. The statistics, compiled after the war, were striking. More than 22 million proximity fuses had been manufactured. They were used in anti-aircraft shells, artillery shells, rockets, and bombs. In the Pacific Naval War alone, proximity-fused ammunition was credited with destroying more than 200 Japanese aircraft in the final 7 months of the war. The total number of Axis aircraft destroyed by proximity-fused weapons, across all theaters, likely exceeded 1,000. But the human cost of developing and deploying this technology was rarely discussed in the immediate post-war period. The focus was on victory, on technological triumph, on American ingenuity solving impossible problems. Dr. Merle Tuve returned to civilian research after the war. He continued his work on cosmic rays and the ionosphere. He rarely spoke publicly about the proximity fuse project, despite its significance. When asked about it in interviews, he would typically give brief, factual answers and then change the subject. In a 1950 interview with a scientific journal, the interviewer pressed him on the moral dimensions of having developed a weapon that had killed so many people. Tuve was quiet for a long moment before answering. "I think about the sailors who survived because their ship's guns could destroy attacking aircraft before those aircraft could crash into them," he said. "I think about the soldiers whose lives were saved because enemy infantry formations were broken up by artillery that worked more effectively than anyone thought possible. I am glad I helped save those lives. But I also think about the young Japanese pilots who were killed by shells I helped design. I think about German soldiers, many of them conscripts who had no desire to be in that war, who died because artillery had become more lethal. I helped make war more efficient at killing. I did it because I believed American democracy needed to survive, and that required winning the war as quickly as possible. I don't regret my decision, but I will never celebrate it." James Van Allen, who had spent countless hours developing the vacuum tubes that made the proximity fuse possible, returned to academic research after the war. He continued working in physics, eventually joining the faculty at the University of Iowa. In the 1950s, he designed scientific instruments for the early American space program. His instruments, carried aboard Explorer 1, America's first satellite, launched in 1958, discovered the radiation belts around Earth that now bear his name. The Van Allen belts are regions of charged particles trapped by Earth's magnetic field. They're a natural phenomenon, pure science with no military application. Van Allen seemed to find satisfaction in this work studying the universe for the sake of understanding, not for building weapons. But he never entirely escaped the proximity fuse. When he was introduced at scientific conferences, the introduction often mentioned his wartime work. His obituary, published when he died in 2006 at age 91, devoted multiple paragraphs to the proximity fuse project before discussing his later scientific achievements. In his private papers, discovered after his death, he had written extensively about his feelings regarding the weapon work. One passage stood out. "I was 26 years old when I joined Section T. I was excited by the engineering challenge. I wanted to solve a problem that had been declared unsolvable. I succeeded. I built vacuum tubes that survived forces that should have destroyed them. I'm proud of my engineering achievement. But I was building them so they could be placed in shells that would kill people. That was the purpose. Not to advance science, not to explore nature, but to kill more effectively. Young men, pilots my own age, died because I figured out how to make glass tubes stronger. That reality sits with me, decades later. I justified it then by telling myself it would save American lives and shorten the war. Both of those things are probably true. But the justification doesn't erase the reality of what I helped create." Lloyd Berkner, who had solved the battery problem, went on to have a distinguished career in science policy and administration. He played a significant role in the International Geophysical Year of 1957 and 1958, a coordinated international scientific effort that included the launch of the first artificial satellites. He served on numerous government advisory boards and helped shape American science policy during the early Cold War period. In his memoirs, published in the 1960s, he wrote about the proximity fuse project. "We were given an impossible task, and we made it possible. I'm proud of what we accomplished technically." The self-activating battery was a genuine innovation, using the force of gun launch to create the power source the fuse needed. It was elegant engineering. But we were not building it for elegance. We were building it so that shells could kill aircraft and the men flying them. We were building it so that artillery could kill infantry more efficiently. That was the mission. We succeeded at the mission. Whether the world is better for that success is a question I cannot answer. The proximity fuse established several precedents that shaped weapons development for the rest of the 20th century and beyond. First, it demonstrated that civilian scientists and engineers, working in university-affiliated research centers, could solve military problems that traditional military laboratories had been unable to solve. This model of mobilizing academic expertise for defense research became standard practice. The Applied Physics Laboratory continued to exist after the war, conducting research on missiles, space systems, and other defense technologies. Similar organizations, like Lincoln Laboratory at MIT and the Rand Corporation, were established following the APL model. Second, the proximity fuse showed that sophisticated electronics could be ruggedized to work in extreme environments. This opened the door to guided missiles, smart bombs, and eventually all the precision-guided weapons that define modern warfare. The techniques developed for making vacuum tubes survive gun launch for protecting delicate electronics from shock, vibration, and acceleration became foundational knowledge for the missile age. Third, the proximity fuse demonstrated the strategic importance of sensors. The shell didn't just fly ballistically and explode at a predetermined time. It sensed its environment, detecting the presence of a target and responding automatically. This principle of weapons that sense and respond, rather than simply following pre-programmed trajectories, became central to military technology. Modern air defense missiles, anti-ship missiles, and precision munitions all incorporate sophisticated sensors. The proximity fuse was, in a meaningful sense, the first smart weapon. Not intelligent in any true sense, it had no computer, no complex decision-making capability. But it was aware of its environment in a limited way, and it responded to that awareness automatically, without human intervention. This represented a fundamental shift in the nature of weapons. For all of human history, weapons had been tools, extensions of human capability that did exactly what they were designed to do with no independent action. A sword cuts when you swing it. A bullet flies when you fire it. An artillery shell explodes when its timer runs out. The proximity fuse was different. You fired it, and then it made a decision when to explode based on information it gathered. That decision happened in milliseconds, far too fast for human reaction time. The weapon was, in a limited but real way, autonomous. This raised questions that would become increasingly important in subsequent decades. What is the proper role of autonomous weapons? How much decision-making authority should be delegated to machines? Where is the boundary between a tool and an independent actor? The proximity fuse was seen simply as a better fuse, more effective than what came before, but it established a pattern that would accelerate throughout the Cold War and beyond. Weapons becoming more sophisticated, more capable of independent action, more able to sense and respond without human guidance. Today, proximity fuses are ubiquitous in military arsenals. Air defense missiles use them, artillery shells use them, anti-tank weapons use them. The basic principle, detect the target, detonate when close enough, has been refined and improved, but it remains fundamentally the same as what Fuze's team developed in 1941 and 1942. Modern proximity fuses use solid-state electronics instead of vacuum tubes. They use advanced signal processing to discriminate between targets and background clutter. They can function in environments with electronic countermeasures and jamming, but they're still doing what the Mark 32 proximity fuse did in 1943, sensing when a target is nearby and triggering detonation at the optimal moment. The technology has also found peaceful applications. Industrial sensors use proximity detection. Automotive safety systems use similar principles for collision avoidance. Even the automatic doors at grocery stores use a form of proximity sensing, detecting when someone approaches and responding by opening. But the original purpose, the reason proximity fuses were developed, was to kill more effectively. That purpose drove billions of dollars in investment and employed thousands of scientists and engineers. It produced a technology that saved lives by ending them, that defended ships by destroying aircraft, that protected ground forces by making artillery more lethal. This is the fundamental paradox of military technology. It is created to protect, but it protects through destruction. The proximity fuse saved American lives. It also took Japanese and German lives. Both of these statements are true. Neither cancels out the other. In 1993, on the 50th anniversary of the first combat use of the proximity fuse, the Naval Historical Center organized a small symposium. Several veterans who had served on ships that used proximity-fused ammunition attended. A few of the surviving scientists from the original APL team were present, including James Van Allen, then 78 years old. A reporter asked Van Allen if he was proud of his contribution to the proximity fuse. Van Allen was silent for a long moment. People in the room shifted uncomfortably, waiting for him to speak. Finally, he said, "Pride is not the word I would use. I am satisfied that I did my duty. I am glad that I helped defend my country and that I helped save the lives of American servicemen. But I am also aware that my work contributed to the deaths of enemy pilots and soldiers, many of them young men like I was, caught up in a war they didn't start and couldn't control. I have spent the rest of my life working on science that has no military application, studying cosmic rays, exploring space, trying to understand the universe. That work brings me pride. The proximity fuse brings me a complicated set of feelings that I don't think I can adequately describe." Another person in the room, a retired Navy captain who had commanded a destroyer at Okinawa, spoke up. "Dr. Van Allen, you need to understand something. That weapon you helped create saved my life and the lives of my crew. We faced kamikaze attacks for months. Without proximity fuses, we would not have survived. You gave us a fighting chance. From those of us who made it home because of your work, thank you. Van Allen nodded slowly. You're welcome. And I mean that. But it doesn't change the complexity of what was done. We built something that killed efficiently. That it saved lives in the process doesn't make it simple. The demon shell, as Japanese pilots called it, was not supernatural. It was technology, brilliant engineering, the result of thousands of hours of work by talented people solving difficult problems. But to the men who faced it in combat, who watched aircraft explode at impossible distances, who saw shells burst at exactly the right moment without any visible reason, it might as well have been supernatural. Their understanding of how warfare worked, of how anti-aircraft defenses functioned, could not accommodate what they were experiencing. The proximity fuse represented something genuinely new in warfare, a weapon that sensed its target and responded automatically at speeds far beyond human capability. It was a glimpse of a future where weapons would become increasingly autonomous, where the human role in combat would shift from direct action to supervision of systems that made their own tactical decisions. That future has arrived. Modern warfare is full of proximity fuses, in various forms, missiles that guide themselves to targets, bombs that detect ground proximity and detonate at optimal altitude, defensive systems that identify threats and engage automatically. The principles established by Fuze, Van Allen, Berkner, and their colleagues in the early 1940s are now foundational to military technology. But the moral questions they grappled with about the responsibility of scientists and engineers who create weapons, about the cost of military effectiveness, about the human consequences of technological advancement remain unresolved. Perhaps they are unresolvable. Perhaps they are questions each generation must answer for itself in the context of the threats it faces and the tools it chooses to build. The proximity fuse saved lives by taking them. It defended freedom by making death more efficient. It represented human ingenuity applied to the problem of destroying other humans more effectively. It was, by any measure, one of the most successful weapons developments of World War II. Whether that success should be celebrated or mourned, or both simultaneously, is a question without a simple answer. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.